opposite to the direction of velocity. Now, since the block is going down the inclined plane, direction of friction will be up the incline. So have a look. We have three forces mg downwards, normal reaction perpendicular to the inclined plane, and the friction, which in this case is kinetic, since the object is actually slipping on the incline. The direction of friction will be opposite to the velocity. So that's the step one, identifying the different forces. Step two, how do we figure out what is the net force acting on this object? So for that, we will break the mg into two components. So the component which is perpendicular to the incline will be mg cos theta, and this particular component will be mg sin theta. And how are we doing this? Because if the angle of inclination is theta, then this particular angle over here is also theta, this small angle. That means the component which is perpendicular to the incline will have the cos parameter, so mg cos theta, and the other component will have the sine parameter, so mg sin theta. So we already know that in situations like this, if a block is kept on an inclined plane, for the block to start moving, there is a critical value of theta which needs to be satisfied, and that is, for the block to start moving, the angle of inclination theta should be greater than tan inverse mu s. Only then the block will start to move. Now, in this case, it is mentioned that the block is actually sliding down the incline, which means the angle of inclination is much greater than tan inverse mu s. So now we have to figure out the magnitude of acceleration using the Newton's second law, F is equal to ma. So acceleration will be equal to the net force divided by m. So what is the net force acting on this object? So if you analyze this picture, the normal reaction will cancel out mg cos theta. So there is zero acceleration perpendicular to the incline, but there is an acceleration along the incline. So we have one force mg sin theta going downwards and the kinetic friction going upwards. Since both these forces are in the opposite direction, we will need to subtract it. So mg sin theta minus kinetic friction will be the value of net force. So F net is mg sin theta minus Fk. And the formula for friction, if you remember, is mu times the normal reaction. And in this situation, the normal reaction is actually equal to mg cos theta. So if we combine these two expressions, so the friction will be mu times mg cos theta, which we can put in the formula. So the net force will be mg sin theta minus friction, which will be mu times mg cos theta. So that is the net force. Now we will divide the net force with mass to get the acceleration. Hence, acceleration is F net upon m. So the entire expression needs to be divided with m. And now if we simplify, we will get acceleration as g sine theta minus mu times g cos theta. So this is the acceleration of a block which is sliding down an inclined plane. So let's summarize. Whenever we have questions which deal with blocks which are sliding down an inclined plane, we need to remember the direction of acceleration is always along the incline and going downwards, and the magnitude will be g sine theta minus mu times g cos theta. This is assuming that the inclined plane is rough, so which means friction is there. Imagine a situation if the inclined plane is smooth, so there is no friction at all. In that case, we can take the value of mu as 0. Mu 0 means it's a frictionless surface. Then the value of acceleration will be just g sine theta. So depending on whether the incline is having friction or it doesn't have friction, the value of acceleration will change. So these are the magnitudes. Now, the direction of acceleration in this case is down the plane. So, coming back to the question, now you can easily say that the acceleration will be g sine theta minus mu g cos theta. There will be a minus sign in the middle because the block is sliding down the incline. And hence, A is the answer for this question. So, here we have a stationary ball which is hanging from a light string. A pellet from an air rifle is traveling horizontally and it becomes embedded in the ball. That means the pellet has gone inside the ball. Velocity of the pellet when it strikes the ball is 160 meters per second. So in the image, we can see that the pellet is just about to enter the ball. So at this stage, let's draw an arrow. The speed just before colliding into the ball, that is 160 meters per second. Then the mass of the ball and the pellet are given. We need to figure out the speed of the ball and the pellet immediately after the impact, once the pellet goes into the ball. So, how do we solve such questions? We will use the law of conservation of momentum, which states that the initial and the final momentum of a system are equal if there is no net force acting on the system. So, in this case, we have to consider pellet plus ball as one system. So, the initial momentum of the pellet ball system needs to be equal to the final momentum of the pellet ball system afterwards. So, let us write momentum before PB would stand for momentum before the collision will be equal to momentum afterwards. So, initially, before the collision, the pellet was traveling with a speed of 160, but the ball was stationary. So, initial momentum of the pellet will be mass is 2 grams, velocity is 160. So, let's write it down. 2 grams, let's convert that into kilograms. This is the mass of the pellet multiplied by the speed of the pellet is 160. Plus, the ball, on the other hand, was stationary. So, we can straight away write the momentum of the ball is 0. So, this is the total momentum of the pellet ball system before the collision. Afterwards, the pellet goes inside the ball. So, pellet and the ball together will be moving as one system. So, mass of the combined pellet ball system will be, let's add them, 250 plus 2 will give us 252 grams. So, the mass will be 252. Let's convert that into kilograms multiplied by V. So V is that speed which we are supposed to find. Speed of the ball and the pellet immediately after the impact, that is V. So all we need to do is just simplify this equation. And if we solve this, we will get the value of V as 1.27 meters per second, which means initially the pellet was traveling at a 160 meter per second speed. Afterwards, when the pellet goes inside the ball, then speed of the ball and the pellet after the impact is 1.27 meters per second, which we can round it to two significant figures to 1.3 meters per second. And that's the answer for part A. Now, in the second part of the question, we need to figure out why the combined kinetic energy of the ball and the pellet after the impact is less than the initial kinetic energy of the bullet. So, without actually doing the calculations, we need to prove how is the combined kinetic energy after the collision is lesser than the initial kinetic energy. Initially, we know that the pellet was traveling with a speed of 160 meters per second. So, of course, it has kinetic energy. Afterwards, the pellet and ball move as one system. So, even after the impact, the pellet and ball does have some kinetic energy. Now, just to explain this in the most simplistic fashion, let's say initial kinetic energy of the pellet before it got embedded in the ball, let's say was 100 joules. Now, afterwards, imagine when the pellet goes inside the ball, the pellet is going to deform the ball. That's one possibility. Second possibility is once the pellet hits the ball, you might be able to hear some sound. So, sound energy comes into the picture. Or there is one more possibility. Once the pellet hits the ball, some sort of sparking might occur, which means heat and light energy can come into the picture. So, where is all of that energy is coming from? So, imagine if the bullet was originally traveling with a total energy of 100 joules, out of which some energy will be used up as either heat energy, light energy, or sound energy. And whatever energy is left, that is the energy which the pellet ball system have after the collision, after the pellet gets embedded into the ball. So here, let's say initial pellet energy was 100 joules, and let's say 30 joules, for example, is wasted as either heat energy, light energy, sound energy, etc. Remaining energy will be 70 joules. So from this, we can say that the initial kinetic energy will always be greater than the final kinetic energy. Now, let me show you the official IB answer. How are we supposed to write this since it's a two marker? So, in the IB solution, it's mentioned like this: work is done by the contact forces to penetrate, deform, squash, or change the shape of the ball. So, this is the same thing which I said earlier. Once the pellet goes into the ball, the pellet is going to deform the shape of the ball. That, of course, requires energy. And then it states this requires energy transfer from kinetic to other forms. And those forms could be potential energy since the shape of the ball can change. So, potential energy or like we discussed earlier, heat energy, light energy, or sound energy, any form. Some part of that energy will be used up and dissipated into the environment, either as sound, light, heat energy, etc. And that is why the final energy will be initial energy minus the wasted energy. And that is why we say that the combined kinetic energy of the ball and the pellet after the impact is less than the initial kinetic energy of the pellet. And that's how we solve the B part of this question. In the C part of the question, it says that the ball with the embedded pellet then rises to a maximum vertical height h. So in the previous case, we had deduced that the velocity of the combined ball pellet system, that velocity v was 1.27 meters per second. We had calculated that. Now, just after impact, the entire system is moving upwards. So since this ball